30 facts about space, according to Science you've never heard. Close your eyes for a moment and imagine this. You're standing in the middle of an empty desert at night. The sky stretched above you like an infinite canvas of diamonds scattered across black velvet. You feel small, don't you? Insignificant, perhaps. But what if I told you that the emptiness you're staring at isn't empty at all? What if I told you that space, that vast void we've gazed at for millennia, is hiding secrets so strange, so utterly bizarre, that they challenge everything we think we know about reality itself? What if the darkness above isn't a void but a stage for the most spectacular, terrifying, and beautiful phenomena in existence? Tonight, we're going to journey beyond the comfortable boundaries of our planet and dive into 30 facts about space that will fundamentally alter how you perceive the universe. These aren't the facts you learned in school. These are the whispers from the edge of reality, the discoveries that keep astronomers awake at night, the truths that make us question whether we truly understand anything at all. Let's begin with something that will make you reconsider the very ground beneath your feet. Right now, as you're listening to these words, you're moving through space at approximately 1.3 million miles per hour. Think about that for a moment. Not standing still, not gently rotating, hurtling. The Earth spins on its axis at roughly 1,000 miles per hour at the equator. We orbit the Sun at about 67,000 miles per hour. But the Sun itself, dragging our entire solar system with it, races around the center of the Milky Way galaxy at roughly 500,000 miles per hour. And the Milky Way? It's speeding through the universe at approximately 1.3 million miles per hour, pulled by gravitational forces we're still trying to fully understand. You've never felt this movement, have you? Your coffee sits still in its cup. Birds fly normally. Everything seems calm, stable, stationary. But you're on a cosmic bullet train, and you didn't even buy a ticket. How does that make you feel about the stability of your world? Here's something even more unsettling. Space is completely silent. Not quiet, not peaceful. Silent in a way that's impossible to truly comprehend here on Earth. Sound needs a medium to travel through, molecules of air or water to vibrate and carry waves to your ears. In the vacuum of space, there are so few particles that sound simply cannot exist. If you could somehow survive in space without a suit and scream at the top of your lungs, you wouldn't hear yourself. An explosion could happen right next to you, a massive destructive force that would tear you apart, and it would happen in absolute, perfect silence. Every space movie you've ever watched with its thundering explosions and roaring engines has been lying to you. The universe conducts its most violent events in a silence more profound than anything you've ever experienced. Imagine the loneliness of that silence. Imagine floating in a void where even your own voice is stolen from you before it can reach your ears. But let's talk about something you can see, or rather, something you can't see but that makes up most of the universe. Dark matter and dark energy together constitute approximately 95% of everything that exists. Read that again. 95%. Everything we can see, touch, measure, and interact with, every star, every planet, every galaxy, every atom in your body, every thought in your head, all of it makes up only 5% of the universe. The rest? We don't know what it is. We call it dark because it doesn't emit, absorb, or reflect light. We know it exists because we can see its gravitational effects on visible matter. Galaxies rotate in ways that shouldn't be possible based on the mass we can see. Something invisible is holding them together, adding mass we cannot detect. Dark energy is even stranger. It's pushing the universe apart, making space itself expand at an accelerating rate. Think about what this means. We live in a universe where we understand only a tiny fraction of what's actually there. It's like trying to understand an elephant by examining only its toenail. Does this make you wonder what else might be invisible to us? What other fundamental aspects of reality might we be completely blind to? Now, let's venture to one of the most terrifying objects in the known universe: the black hole. You probably know the basics. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. But here's what makes them truly nightmarish. If you were to fall into a black hole, you would experience something called spaghettification. The gravitational force at your feet would be so much stronger than at your head that you would be stretched like taffy, your body elongated into a thin stream of atoms. But here's the really disturbing part. Because of time dilation, from your perspective, you might experience this stretching relatively quickly. But to someone watching from a safe distance, you would appear to slow down as you approach the event horizon, your image becoming redder and dimmer, frozen in time, taking an eternity to actually cross that boundary. You would watch the universe age while you slowly, from an outside perspective, become a permanent frozen image on the edge of the black hole. Which version is real? Both, depending on your frame of reference. Time itself becomes relative near these cosmic monsters. And speaking of black holes, scientists have discovered something absolutely mind-bending. There are supermassive black holes at the centers of most galaxies, including our own Milky Way. The one at our galactic center is called Sagittarius A star, and it has a mass equivalent to approximately 4 million suns, all compressed into a region smaller than our solar system. 4 million suns worth of matter in a relatively tiny space. But here's the extraordinary part. In 2019, scientists captured the first actual image of a black hole's event horizon in the galaxy Messier 87. This black hole has a mass of 6.5 billion suns. To put that in perspective, if this black hole were placed where our sun is, its event horizon would extend beyond the orbit of Neptune. It's an abyss so massive that our minds struggle to grasp it. And it's real. It exists. Right now, as you listen to this, that monster is out there, feeding on stars and gas and anything unlucky enough to drift too close. How many other cosmic terrors are lurking in the darkness, waiting to be discovered? Let me tell you about something called the Great Attractor. In the direction of the constellations Hydra and Centaurus, roughly 150 million light-years away, there's something massive pulling our galaxy and thousands of others toward it. We can't see it directly because it's obscured by the plane of our own Milky Way, hidden behind dust and stars. But we know it's there because we can measure the movement of galaxies being pulled in that direction. The Milky Way, along with everything in our local group of galaxies, is falling toward this invisible gravitational anomaly at a speed of about 14 million miles per hour. We think it might be a massive concentration of mass, perhaps a supercluster of galaxies, but we can't be certain. Something immense is pulling us through space, and we're largely blind to what it actually is. Doesn't that make you feel like a passenger on a ship being pulled toward an unseen destination? Here's a fact that will change how you look at stars. When you gaze up at the night sky, you're not seeing the present. You're seeing the past. Light takes time to travel, and distances in space are so vast that the light from stars takes years, centuries, sometimes millions of years to reach your eyes. The light from the nearest star system, Alpha Centauri, takes about 4.3 years to reach us. We see it as it was 4.3 years ago. Some of the stars you see might have already exploded, died, collapsed into black holes, but their light is still traveling through space and won't reach us for years or centuries. You might be looking at a star that no longer exists. The night sky is a museum of cosmic history, each point of light a timestamp from a different era. When you look at the Andromeda Galaxy, visible to the naked eye on a clear night, you're seeing it as it was 2.5 million years ago, long before humans walked the Earth. You're a time traveler every time you look up. Have you ever considered that the present moment, the now, is different everywhere in the universe? Let's discuss temperature extremes. The coldest place we found in the universe is the Boomerang Nebula, a cloud of gas expelled from a dying star about 5,000 light-years from Earth. Its temperature is approximately 1 degree Kelvin, or negative 458 degrees Fahrenheit. That's colder than the cosmic microwave background radiation, the leftover heat from the Big Bang that permeates all of space. How is this possible? The gas in the Boomerang Nebula is expanding so rapidly that it cools faster than it can absorb radiation from the surrounding space. It's nature's refrigerator, a pocket of extreme cold in the vastness of space. But let's flip to the other extreme. The hottest temperature ever created in the universe, as far as we know, occurred at the moment of the Big Bang, when temperatures reached an incomprehensible 10 to the power of 32 Kelvin. But in more recent cosmic history, the cores of massive stars undergoing supernova explosions can reach temperatures of about 100 billion Kelvin. At these temperatures, atoms don't exist as we know them. Matter itself behaves in ways that seem alien. The universe is a place of extremes that make our hottest deserts and coldest tundras seem mild by comparison. Now let me tell you about something called quantum entanglement and how it relates to space. Einstein called it spooky action at a distance, and he was deeply troubled by it. When two particles become entangled, they remain connected in a way that defies our understanding of space and distance. If you measure the state of one particle, the other particle, no matter how far away it is, even on the opposite side of the universe, instantly reflects a corresponding state. Not after a delay, instantly. This doesn't violate the speed of light because no information is technically being transmitted, but it suggests that at a quantum level, space and distance might not mean what we think they mean. The universe might be connected in ways that transcend our three-dimensional understanding of reality. Some physicists speculate that entanglement might be a clue to understanding the fabric of space-time itself, that space might emerge from quantum entanglement rather than being a fundamental backdrop. What does it mean if distance is an illusion? If separation is not as absolute as it appears? Here's something that sounds like science fiction but is absolutely real. There are stars in the universe called neutron stars that are so dense that a single teaspoon of their material would weigh about 6 billion tons on Earth. When a massive star explodes in a supernova, its core can collapse into a sphere only about 12 miles in diameter, but containing more mass than our Sun. The gravity is so intense that protons and electrons are crushed together to form neutrons, creating matter in a state that doesn't exist anywhere on Earth. The surface gravity is about 2 billion times stronger than Earth's. If you could somehow stand on a neutron star, which you absolutely couldn't, you would weigh billions of times more than you do now, and you'd be instantly flattened into a layer of atoms about 1 atom thick. Some neutron stars spin hundreds of times per second, creating beams of radiation that sweep across space like cosmic lighthouses. We call these pulsars, and their timing is so precise that scientists have considered using them as natural cosmic clocks. The universe has created matter so dense that it breaks our everyday understanding of what solid means. Let me share something about the scale of the universe that might make your head spin. The observable universe, the part we can potentially see, is about 93 billion light-years in diameter. That's the distance light has traveled in all directions since the Big Bang, accounting for the expansion of space. But here's the crucial detail. The universe is only about 13.8 billion years old. How can the observable universe be 93 billion light-years across if it's only 13.8 billion years old? Because space itself has been expanding. The galaxies at the edge of our observable universe didn't travel through space to get there. The space between us and them expanded. And here's the really mind-bending part. The observable universe is almost certainly just a tiny fraction of the entire universe. The universe might be infinite. Think about that. Infinite. Truly endless. Or it might be finite but unbounded, curving back on itself in dimensions we can't visualize. There could be galaxies, countless trillions of them, beyond our cosmic horizon that we will never, ever be able to see because the expansion of space is carrying them away faster than light can travel to reach us. There are parts of the universe forever beyond our reach, forever unknowable. Let's talk about something called Hawking radiation, named after Stephen Hawking. For a long time, scientists believed that nothing could escape a black hole once it crossed the event horizon. But Hawking proposed something revolutionary. At the quantum level, near the event horizon, particle-antiparticle pairs constantly pop into existence and annihilate each other. This happens everywhere in space, but near a black hole's event horizon, one particle might fall into the black hole while its partner escapes. From an outside perspective, it appears that the black hole is emitting radiation. Over immense timescales, this process could cause black holes to slowly evaporate, losing mass until they eventually disappear in a final burst of energy. This means black holes aren't eternal. They're temporary, at least on cosmic timescales. A stellar mass black hole might take 10 to the power of 67 years to evaporate, a number so large it's meaningless to human comprehension. But it means that in the unimaginably distant future, even these cosmic monsters will fade away. The universe is stranger than we imagine. Even the most permanent seeming objects are temporary. Here's a disturbing thought about space exploration. Space is full of debris traveling at incredible speeds. In low Earth orbit, there are millions of pieces of space junk, fragments of old satellites, paint flecks, bits of rockets, all traveling at speeds up to 17,500 miles per hour. At that speed, even a tiny paint chip has enough kinetic energy to damage a spacecraft. A piece of debris the size of a marble could punch through the hull of the International Space Station. And we're constantly adding more debris. Every satellite we launch, every rocket that breaks apart, adds to this cloud of high-speed shrapnel orbiting our planet. There's a theoretical scenario called Kessler syndrome, where the density of objects in orbit becomes so high that collisions create cascading effects, each collision creating more debris, leading to more collisions, until low Earth orbit becomes too dangerous to use. We could trap ourselves on our own planet, unable to safely launch satellites or spacecraft through the debris field we created. Are we building our own cage? Let me tell you about the cosmic microwave background radiation, the afterglow of the Big Bang. In every direction we look, we can detect this faint microwave radiation, the stretched and cooled remnant of the intense heat from the universe's birth. It's everywhere, a constant whisper from the beginning of time, and it's surprisingly uniform, varying in temperature by only about 1 part in 100,000. This uniformity is both reassuring and puzzling. How did regions of space that could never have been in contact with each other, that couldn't have exchanged heat or energy, end up at almost exactly the same temperature? This led to the theory of cosmic inflation, the idea that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, stretching a tiny, uniform region to cosmic scales. It's a theory, one that fits the evidence we have, but it requires us to believe that the universe expanded faster than the speed of light for a brief moment. Space itself can expand faster than light because space isn't moving through anything. It's the fabric itself stretching. We're living in the echo of an event so violent and rapid that it defies intuition. Now, consider this fact about time. Time doesn't pass at the same rate everywhere in the universe. According to Einstein's theory of general relativity, gravity warps spacetime, and stronger gravitational fields cause time to pass more slowly. This isn't theoretical. It's measurable. Atomic clocks at sea level run slightly slower than atomic clocks on mountaintops because they're deeper in Earth's gravitational well. GPS satellites have to account for this time dilation, or they'd quickly become inaccurate. On the surface of a neutron star, time would pass noticeably slower than on Earth. Near the event horizon of a black hole, time dilation becomes extreme. If you could watch someone approach a black hole, you'd see them slow down, their movements becoming more and more sluggish as they got closer, until they appeared to freeze at the event horizon, taking an infinite amount of time, from your perspective, to cross it. But from their perspective, they'd cross it in finite time and continue falling. There's no universal now, no cosmic clock ticking the same for everyone everywhere. Time is local, personal, relative. Does this change how you think about the present moment? Let's venture into the realm of speculation for a moment. Some cosmologists propose the idea of a multiverse, the concept that our universe might be just one of countless universes, each with potentially different physical laws, different constants, different properties. This isn't fantasy. It emerges from serious interpretations of quantum mechanics and cosmic inflation theory. If space underwent exponential inflation, perhaps it's still inflating in regions beyond our observable universe, and perhaps new pocket universes are constantly budding off, each with its own properties determined by how quantum fields settled during their formation. We might exist in a vast foam of universes, most of them inhospitable to life as we know it, but some, by chance, having the right properties for complexity, for stars, for planets, for life. This is speculation, and we may never be able to test it because these other universes, if they exist, would be forever beyond our observation. But it raises a profound question. If the multiverse exists, is our universe's apparent fine-tuning for life just a selection effect? We exist in this universe because it's one of the rare ones where our kind of life is possible. What do you think? Does the idea of countless other universes make our existence feel more or less meaningful? Here's a fact about our sun that puts our existence in perspective. The sun converts approximately 600 million tons of hydrogen into helium every single second through nuclear fusion. Every second. This process releases an enormous amount of energy, the energy that lights our world and makes life possible. But even at this tremendous rate of fuel consumption, the sun has only converted about half of its hydrogen fuel in the 4.6 billion years it's been burning. It has another 5 billion years or so before it exhausts its hydrogen core and begins to die, expanding into a red giant that will likely engulf Mercury, Venus, and possibly Earth. Our planet's time is limited, not by thousands of years or millions, but by billions. It seems like a long time, but it's finite. The sun that seems eternal, that has been worshipped as a god by countless civilizations, is itself mortal. Eventually, it will swell, cool, shed its outer layers, and fade into a white dwarf, a dense ember slowly cooling over trillions of years. Everything has an ending, even stars. Let me tell you about rogue planets. We usually think of planets as orbiting stars, but there are planets wandering through interstellar space, untethered to any solar system, drifting alone in the cosmic dark. These rogue planets might have formed around stars and been ejected through gravitational interactions, or they might have formed in isolation from clouds of gas and dust. We don't know exactly how many there are, but some estimates suggest there could be billions in our galaxy alone, possibly outnumbering stars. Imagine a planet, perhaps Earth-sized, perhaps larger, tumbling through the void between stars, its surface frozen and lifeless, heated only by internal radioactive decay or tidal forces if it has moons. No sun ever rises on these worlds. They exist in perpetual darkness, wandering the galaxy for billions of years, occasionally passing close enough to a star system to be affected by its gravity, but mostly traveling through empty space. It's a lonely existence for a world. Could life exist on such a planet, perhaps beneath a thick icy shell warmed by internal heat? It's speculation, but the universe is stranger than we imagine. Here's something that will make you appreciate the sun's stability. There are stars called variable stars that change in brightness over time, sometimes dramatically. Cepheid variables, for example, pulse in a regular rhythm, expanding and contracting as they oscillate between different states of equilibrium. Other stars undergo sudden, violent changes. Flare stars release bursts of energy that can increase their brightness by many times in just minutes. If our sun were a flare star, life on Earth would face periodic bursts of radiation that could sterilize the surface. We exist because our sun is relatively stable, a middle-aged yellow dwarf star in a long, steady phase of hydrogen fusion. But not all planets are so fortunate. Exoplanets orbiting variable or flare stars would experience wildly changing conditions. Could life adapt to such an environment? We don't know, but it's another reminder that we live in a cosmic sweet spot, orbiting a star that's remarkably consistent. Now let's talk about something called frame dragging. When a massive object rotates, it actually drags space-time along with it, like a spoon stirring honey. This effect, predicted by general relativity, has been measured around Earth. Satellites have detected the tiny twist in space-time caused by our planet's rotation. But around rapidly spinning black holes, frame dragging becomes extreme. The space-time near a rotating black hole is pulled around so strongly that it's impossible to stand still, even outside the event horizon. There's a region called the ergosphere where you'd be forced to rotate with a black hole, dragged along by the twisting of space itself. You could still escape from the ergosphere, unlike from inside the event horizon, but you couldn't resist the rotation. Space itself would be moving, carrying you with it. This means that a rotating black hole affects a larger region than a non-rotating one. The universe is not just curved by mass. It's twisted by rotation. Space is dynamic, active, responsive to matter and energy in ways that seem almost alive. Let me share a disturbing possibility. The expansion of the universe is accelerating, driven by dark energy. If this acceleration continues, and current evidence suggests it will, the universe faces a fate called the Big Rip. In this scenario, the expansion of space accelerates to the point where it overcomes all forces holding structures together. First, galaxies outside our local group would recede beyond our cosmic horizon, disappearing from view. Then, billions of years later, galaxies themselves would be torn apart, stars scattered into isolation. Planetary systems would be disrupted, planets flung away from their suns. Eventually, even atoms would be ripped apart, space expanding faster than the forces holding matter together. The universe would end in complete dissociation, every particle isolated and alone. This is one possible fate, based on certain assumptions about dark energy. Other scenarios include the Big Freeze, where the universe expands forever, slowly cooling until all stars burn out and everything fades into cold darkness, or the Big Crunch, if some unknown factor reverses the expansion, causing everything to collapse back into a singularity. We don't know which fate awaits the universe, but all current models suggest an ending, in some form, at some unimaginably distant point in the future. How does it feel to know that even the universe itself is temporary? Here's a fact about Mars that's both fascinating and eerie. Mars once had liquid water on its surface. We've found dried riverbeds, lake basins, minerals that only form in the presence of water, evidence of an ancient, wetter climate. But Mars lost most of its atmosphere over billions of years, likely because its weak magnetic field couldn't protect it from the solar wind, which gradually stripped away its air. As the atmosphere thinned, the water evaporated or froze, and Mars became the cold, dry desert we see today. But here's the haunting part. Somewhere between 3 and 4 billion years ago, Mars might have been a world where life could emerge. If it did, what happened to it? Did it die out when the water disappeared? Could it have adapted, retreated underground to environments where liquid water still exists, protected by layers of rock and ice? Right now, beneath the Martian surface, there might be microbial life, descendants of ancient Martian organisms, clinging to existence in isolated pockets of warmth and moisture. Or we might find fossils, evidence of life that bloomed and died billions of years ago. Mars is a cautionary tale about planetary death, a reminder that worlds can change, that atmospheres can be lost, that life's hold on a planet might be more fragile than we'd like to believe. Should this warning worry us about Earth's future? Let me tell you about the Voyager spacecraft, 2 probes launched in 1977 to explore the outer solar system. After completing their primary missions, studying Jupiter, Saturn, Uranus, and Neptune, they continued outward, and they're still traveling. Voyager 1 is now in interstellar space, beyond the influence of the solar wind, more than 14 billion miles from Earth. It's the most distant human-made object. Both Voyager probes carry a golden record, a disk containing sounds and images from Earth, greetings in multiple languages, music from different cultures, a message to any intelligent life that might someday find them. But here's the profound and melancholy part. The Voyagers are traveling so slowly compared to interstellar distances that they won't approach another star system for tens of thousands of years. Long before then, they'll go silent, their power sources depleted, their transmitters dead. They'll drift through the galaxy for millions, perhaps billions of years, ancient artifacts from a species that might no longer exist by the time anyone finds them. They're our message in a bottle. cast into an ocean vaster than imagination. Will anyone ever find them? Will humanity still exist when they do? Or will these tiny spacecraft be our only legacy, silent tombstones orbiting the galaxy long after Earth itself is gone? Now let's discuss something called gravitational waves. In 2015, scientists made one of the most remarkable detections in the history of astronomy. They observed ripples in spacetime itself, gravitational waves caused by the collision and merger of two black holes over 1 billion light-years away. When these black holes spiraled into each other, they released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. The collision warped spacetime so violently that the waves spread outward at the speed of light, stretching and squeezing space itself. When they passed through Earth, they changed the distance between points in space by less than the width of a proton, but our instruments were sensitive enough to detect it. We can now listen to the universe in a new way, detecting events that emit no light, no radiation we can see with telescopes, only these ripples in the fabric of reality. We've opened a new sense, a new way of perceiving cosmic events. What else might we discover now that we can detect what was previously invisible? Here's something that challenges our understanding of matter. In the cores of massive stars, fusion creates heavier and heavier elements, up to iron. But elements heavier than iron require more energy to fuse than they release, so fusion stops. When a star massive enough to have an iron core finally exhausted its fuel, it collapses catastrophically in a supernova, and in the incredible temperatures and pressures of that explosion, heavier elements are formed. Elements like gold, platinum, uranium. Every atom of gold in your jewelry, every atom of silver in your electronics, was forged in the heart of an exploding star billions of years ago, then scattered into space, eventually incorporated into the cloud of gas and dust that formed our solar system. You are made of stardust. This is literally true. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all created in stellar furnaces and supernova explosions. We are the universe becoming aware of itself. We are matter that has learned to think, to wonder, to look back at the stars and realize our origin. Does knowing this change how you see yourself? Let me share something about Jupiter that's both protective and terrifying. Jupiter, the largest planet in our solar system, acts as a cosmic shield for the inner planets. Its immense gravity deflects or captures comets and asteroids that might otherwise strike Earth. Some scientists believe that without Jupiter, Earth would be bombarded far more frequently by large impacts, possibly preventing complex life from evolving. Jupiter has taken hits for us. In 1994, astronomers watched as comet Shoemaker-Levy 9 broke apart and slammed into Jupiter in a series of impacts, each releasing energy equivalent to millions of nuclear bombs. The scars in Jupiter's atmosphere were visible for months. That could have been Earth. But here's the disturbing part. Jupiter's gravity also occasionally flings objects inward toward the inner solar system. It's not a perfect shield. It's more like a gravitational pinball machine, sometimes redirecting threats, sometimes creating them. Our existence might depend on a delicate balance of gravitational influences that have, so far, kept the worst impacts at bay. How much of our survival is luck? Now consider the cosmic speed limit. The speed of light in a vacuum, approximately 186,000 miles per second, appears to be the universe's absolute speed limit. Nothing with mass can reach or exceed this speed. As you accelerate, your mass effectively increases, requiring more and more energy to go faster, approaching infinite energy required to reach light speed. This isn't just a limitation of our technology. It's a fundamental property of the universe. But this limit creates a problem for space exploration. The nearest star system, Alpha Centauri, is about 4.3 light-years away. Even traveling at light speed, which is impossible for anything with mass, it would take 4.3 years to get there. The Milky Way galaxy is about 100,000 light-years across. Traveling at light speed, it would take 100,000 years to cross it. The distances are so vast that even at the cosmic speed limit, the universe remains largely inaccessible, unless we find a loophole. Some physicists speculate about possibilities like warp drives, which wouldn't move a ship through space faster than light but would contract space in front of the ship and expand it behind, effectively moving the ship faster than light relative to distant points without violating relativity. Or wormholes, hypothetical shortcuts through space-time connecting distant points. These concepts are consistent with general relativity under certain conditions, but they require exotic matter with negative mass energy, which may not exist. The universe teases us with its vastness while imposing limits on how we can explore it. Are we meant to remain confined to our tiny corner of space? Let me tell you about something called the WOW signal. In 1977, a radio telescope in Ohio detected a strong narrowband radio signal apparently coming from space. It lasted 72 seconds, and it was so unusual, so unexpected, that the astronomer who noticed it wrote, "Wow," on the printout. The signal appeared to come from the direction of the constellation Sagittarius, and it had characteristics consistent with an artificial signal rather than natural radio emissions. It has never been detected again despite numerous attempts to find it. Was it a signal from an alien civilization? A natural phenomenon we don't understand? A satellite or aircraft that coincidentally matched what we'd expect from an interstellar signal? We don't know. The WOW signal remains one of the most intriguing mysteries in the search for extraterrestrial intelligence. It's a reminder that the universe might be trying to tell us something, and we're struggling to understand the message. What if we're surrounded by signals we don't know how to interpret? What if intelligence is common in the universe, but communication across the void is harder than we imagine? Here's a chilling fact about Venus. Often called Earth's sister planet because of its similar size, Venus is a hell's cape. The surface temperature is about 900 degrees Fahrenheit, hot enough to melt lead, maintained by a runaway greenhouse effect. The atmosphere is 90 times denser than Earth's and composed mostly of carbon dioxide with clouds of sulfuric acid. The pressure at the surface would crush you, and the heat would incinerate you, and the atmosphere would corrode any remains. But Venus might not have always been this way. Some scientists believe Venus might once have had oceans, a more Earth-like climate, but a runaway greenhouse effect boiled away the water, the hydrogen escaped to space, and the planet transformed into the inferno we see today. This raises a terrifying question. Could Earth go the way of Venus? If we pump enough greenhouse gases into our atmosphere, if we trigger certain feedback loops, could our planet undergo a similar transformation? Venus is what Earth could become under the wrong conditions. It's a warning etched in planetary science, a cautionary tale orbiting just next door. Let's talk about cosmic voids. The universe is not uniformly distributed. Galaxies cluster together along filaments and sheets, forming a cosmic web. Between these structures are enormous voids, regions hundreds of millions of light years across containing very few galaxies. These voids are the largest structures in the universe, vast bubbles of emptiness. Traveling through one of these voids, you'd see almost no galaxies in any direction for millions of light years. The scale is incomprehensible. Our entire observable universe would be just a fraction of one of these voids. What would it feel like to be conscious in the middle of such emptiness, knowing that in every direction for millions of light years, there's almost nothing? The cosmic voids are the universe's empty rooms, spaces so large that our minds cannot truly grasp them. They remind us that the universe is mostly empty, that matter is the exception, not the rule, and that the darkness between the lights is far more vast than the lights themselves. Now let me share something that sounds impossible. There are moons in our solar system that might harbor life. Europa, one of Jupiter's largest moons, is covered in ice, but beneath that ice, there's strong evidence for a global ocean of liquid water, kept warm by tidal heating as Jupiter's gravity flexes and kneads Europa's interior. This ocean might contain more water than all of Earth's oceans combined. And where there's liquid water, heat, and chemical nutrients, there might be life. Enceladus, a small moon of Saturn, also has an icy surface and an underground ocean. We've seen geysers erupting from its south pole, shooting water vapor and ice particles into space. Some of these particles fall back to the surface, but some escape, forming one of Saturn's rings. Scientists have analyzed the composition of these geysers and found organic molecules, the building blocks of life. Titan, Saturn's largest moon, has lakes and seas of liquid methane and ethane on its surface and a thick atmosphere. While it's too cold for liquid water on the surface, there might be a water-ammonia ocean beneath the ice. Could life exist in these exotic environments? Could there be microbes in Europa's ocean, swimming in eternal darkness under miles of ice? The solar system, our immediate neighborhood, might be teeming with life in forms we've never imagined. Are we alone, or are we surrounded by alien ecosystems right here in our own cosmic backyard? Here's a fact that illustrates the violence of the universe. Gamma-ray bursts are the most energetic events known to occur since the Big Bang. They're brief flashes of gamma rays, the most energetic form of light, lasting from milliseconds to several minutes, but releasing more energy than the sun will emit in its entire 10 billion-year lifetime. We think they're caused by the collapse of massive stars into black holes or by the collision of neutron stars. These explosions are so powerful that if one occurred within a few thousand light-years of Earth and was aimed in our direction, the gamma rays could strip away our ozone layer, expose the surface to deadly ultraviolet radiation, and trigger a mass extinction. In fact, some scientists speculate that a gamma-ray burst might have caused the Ordovician extinction event about 450 million years ago, though this remains unproven. The universe is not just beautiful and mysterious. It's dangerous, full of events that could sterilize a planet without warning. We exist at the mercy of cosmic chance, hoping that we're not in the wrong place when the universe decides to unleash its fury. Let me tell you about the Great Cold Spot. Scientists have found an unusually cold region in the cosmic microwave background radiation, about 1.8 billion light-years across. This region is about 70 microkelvins colder than the average temperature of the cosmic microwave background. That might not sound like much, but at cosmic scales, it's significant. What could cause such a cold spot? One theory is that it's caused by a supervoid, an enormous region of space with fewer galaxies than average, and photons from the cosmic microwave background lose energy passing through it. Another, more speculative theory is that it could be evidence of a collision between our universe and another universe in the distant past, a bruise on the fabric of spacetime from a cosmic impact. This is highly speculative, and most scientists favor the supervoid explanation, but the mere possibility that we might be seeing evidence of another universe colliding with ours is staggering. The cosmic microwave background is a map of the early universe, and we're still learning to read it. What other secrets might be hidden in its tiny temperature fluctuations? Here's something to ponder. The atoms in your body are almost entirely empty space. If you removed all the empty space from every atom in your body, you'd be smaller than a grain of sand. Atoms consist of a tiny nucleus surrounded by a cloud of electrons, but the distance between the nucleus and the electrons, on an atomic scale, is enormous. Matter feels solid because of the electromagnetic forces between atoms, but it's mostly emptiness. And those nuclei, they're made of protons and neutrons, which are themselves made of quarks held together by gluons. The deeper we look, the stranger matter becomes, less like solid stuff and more like patterns of energy and probability. You are not as solid as you feel. You're a cloud of quantum probabilities, a pattern of energy that has learned to be aware of itself. Does this make you feel more or less real? Let's discuss the Fermi paradox. Given the vastness of the universe, the billions of galaxies each containing billions of stars, many of which likely have planets, and given that the universe is nearly 14 billion years old, where is everyone? If intelligent life is common, we should see evidence of it. Advanced civilizations should be colonizing galaxies, building megastructures, sending out signals. Yet we see no definitive evidence of extraterrestrial intelligence. This is the Fermi paradox, named after physicist Enrico Fermi. There are many proposed solutions. Perhaps life is rarer than we think. Perhaps intelligence is rare. Perhaps civilizations destroy themselves before they become spacefaring. Perhaps they're out there but have no interest in communicating. Perhaps the distances are simply too vast for communication or travel to be practical. Or perhaps they're here and we don't recognize them, or they're deliberately hiding. Some speculate about a great filter, some barrier that prevents civilizations from reaching the point where they're detectable across interstellar distances. If the great filter is behind us, we're incredibly fortunate to have passed it. If it's ahead of us, we might be doomed. The silence of the universe is one of the deepest mysteries we face. Are we alone, or are we just not listening in the right way? Now let me tell you about stellar remnants called white dwarfs. When a star like our Sun exhausts its fuel, it sheds its outer layers and leaves behind its core, which becomes a white dwarf. These objects are about the size of Earth, but contain about half the mass of the Sun. The density is staggering. A teaspoon of white dwarf material would weigh about 15 tons. White dwarfs don't generate energy through fusion. They're just hot remnants, slowly cooling over trillions of years. But here's the strange part. The matter in a white dwarf exists in a state called electron degeneracy. The electrons are packed so tightly that they resist further compression not because of electromagnetic forces but because of quantum mechanical principles. The Pauli exclusion principle prevents electrons from occupying the same quantum state, and this creates a pressure that holds the white dwarf up against gravity. Matter itself behaves differently under these extreme conditions. And if you add more mass to a white dwarf, there's a limit called the Chandrasekhar limit, about 1.4 times the mass of the Sun, beyond which electron degeneracy pressure can't hold it up. The white dwarf collapses further, triggering a runaway nuclear reaction that destroys the star in a type Ia supernova. These explosions are so consistent in brightness that we use them as standard candles to measure cosmic distances. The death of a star becomes a tool for understanding the universe. Here's something that should make you appreciate the atmosphere. Earth's magnetic field and atmosphere protect us from cosmic radiation, high-energy particles from the Sun and from deep space that would be lethal to unprotected organisms. Astronauts in space are exposed to higher levels of radiation, and on long missions, this becomes a serious health concern. On the Moon, with no atmosphere or magnetic field, the radiation exposure is even higher. Mars has only a thin atmosphere and a weak magnetic field, so colonists would face significant radiation exposure. Building habitats on other worlds will require shielding, probably using the local soil or rock to protect inhabitants from this constant bombardment. In space, the universe is actively hostile to life as we know it. We evolved under the protection of Earth's magnetic field and thick atmosphere. Venturing beyond that protection means facing an environment where the universe is trying to kill us with invisible rays. It's a reminder that Earth is not just our home. It's our shield. Let me share something about time and the universe's age. We say the universe is 13.8 billion years old, but that's from our perspective, our reference frame. Because of time dilation, time has passed at different rates in different parts of the universe depending on local gravitational fields and velocities. There's no universal clock that's been ticking since the Big Bang. Time itself is relative. Additionally, looking back toward the Big Bang, we reach a point where our current physics breaks down. At the moment of the Big Bang itself, or rather at the Planck time, about 10 to the negative 43 seconds after the initial singularity, our understanding of space-time becomes meaningless. We don't have a theory that successfully combines quantum mechanics and general relativity at those scales. The very concept of before the Big Bang might be meaningless. Time itself might have begun with the universe. Asking what happened before the Big Bang might be like asking what's north of the North Pole. The question doesn't make sense because there is no north of the North Pole. Time, space, matter, energy, all might have emerged together. Or perhaps our universe is part of an eternal inflationary multiverse where Big Bangs are constantly happening in different regions. We're pushing at the boundaries of what we can know, asking questions that might not have answers, at least not with our current understanding. Here's a fact about Saturn's rings that's both beautiful and melancholic. Those magnificent rings, the most spectacular sight in the solar system, are not permanent. They're young, cosmically speaking, probably only a few 100 million years old, and they're slowly falling into Saturn, raining down on the planet's atmosphere. Scientists estimate that the rings might only last another 100 million years or so before they disappear. We're lucky to exist in an era when Saturn has rings. For most of the solar system's history, Saturn might have been ringless, and in the future, it will be again. The rings might have formed from the destruction of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. Now those fragments orbit the planet in a thin disk, a temporary monument to destruction. The universe is full of temporary beauty, phenomena that exist for just a brief moment on cosmic timescales. The fact that we're here to witness Saturn's rings, that our existence coincides with theirs, is pure chance. What other wonders have come and gone in the universe, unseen by any conscious mind? Let's talk about something called the holographic principle. This is a deep theoretical idea suggesting that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram. In other words, our three-dimensional reality might be a projection of information encoded on a two-dimensional surface. This emerges from studies of black hole thermodynamics and string theory. If true, it means that space might have one less dimension than we perceive, that the depth we see might be an illusion created by information on a distant boundary. This is highly speculative and not proven, but it's taken seriously by theoretical physicists. It suggests that reality might be fundamentally different from what we perceive, that the universe might be stranger and more illusion-like than we ever imagined. If we're living in a holographic projection, does that make us less real? Or does it simply mean that real is different from what we thought? Now, let me tell you about the ultimate fate of stars that are too massive to become white dwarfs. If a star is massive enough, its core will collapse past the point where even neutron degeneracy pressure can hold it up. There's no known force that can stop the collapse. It becomes a black hole, a singularity where all the mass is compressed into a point of infinite density. At least, that's what general relativity predicts. But infinity is a red flag in physics, usually indicating that our theories are breaking down. We don't actually know what happens at the center of a black hole. Some physicists speculate that quantum effects might prevent a true singularity, creating instead some kind of exotic object we don't yet understand. Others propose that the collapsing matter might tunnel through space-time, emerging elsewhere as a white hole, the time reverse of a black hole, spewing out matter. This is pure speculation. The truth is, we don't know what's at the center of a black hole. General relativity says singularity, but general relativity also predicts its own failure at that point. The centers of black holes are places where our understanding of physics breaks. They're cosmic question marks, regions where the universe refuses to tell us what's happening. Here's something that connects to daily life. The GPS system you use to navigate relies on corrections from both special and general relativity. The satellites orbit Earth at high speeds, which causes time dilation from special relativity, making their clocks run slower. But they're also farther from Earth's gravitational field, which causes time dilation from general relativity, making their clocks run faster. The effects partially cancel, but not completely. If we didn't account for relativistic time dilation, GPS would accumulate errors of several miles per day. The fact that your phone can tell you your position within a few meters is proof that Einstein's theories are correct. Relativity isn't just abstract physics. It's in your pocket, making modern technology work. The universe's strange rules, discovered by looking at the stars and thinking deeply about space and time, turn out to be essential for a device you use every day. Let me share one final, haunting fact. There's a boundary in space called the cosmic event horizon, created by the expansion of the universe. galaxies beyond this boundary are receding from us faster than light because the space between us and them is expanding faster than light can travel through it. This means light from those galaxies will never reach us. They're beyond our ability to observe, even in principle. As the universe continues to expand, more and more galaxies will cross this horizon and disappear from view. In the far future, if dark energy continues to drive accelerating expansion, a civilization arising billions of years from now might look out and see only their local group of galaxies. The rest of the universe would have receded beyond the cosmic horizon. They wouldn't see the cosmic microwave background. They wouldn't have the evidence we have for the Big Bang. Their astronomers might conclude that the universe is just their galaxy cluster surrounded by eternal emptiness. They'd be wrong, but they'd have no way to know. This means that our position in time is privileged. We can see evidence of the Big Bang, evidence that will eventually fade away. We exist in a window of cosmic history when the universe's origins are still visible. Doesn't this make you feel a responsibility to look, to learn, to understand while we still can? So where does all this leave us? We've journeyed from the speed at which we're hurtling through space to the ultimate fate of the universe. We've touched on the silence of the cosmos, the monsters lurking in the darkness, the invisible majority of reality, the relativity of time, and the possibility of life on frozen moons right here in our solar system. We've considered the fragility of our existence, protected by a magnetic field and an atmosphere that could be stripped away, living on a planet that could go the way of Venus or Mars. We've marveled at the fact that we're made of atoms forged in the hearts of dying stars, that we're literally the universe aware of itself. We've confronted the vastness of space, the limitations imposed by the speed of light, and the possibility that we're alone, or worse, that we're surrounded by others but unable to communicate. We've seen that time is not absolute, that matter is mostly empty space, that the universe is stranger than we can easily imagine. Space is not just a place. It's a reminder of our smallness and our significance. We're tiny, living on a dust mote orbiting an ordinary star in an unremarkable galaxy in a universe that's mostly empty and dark. And yet, we're capable of understanding it. We've deciphered the laws that govern stars and galaxies. We've looked back in time to the birth of the universe. We've sent our artifacts beyond the solar system to drift among the stars. We've asked profound questions about where we came from and where we're going. We're matter that became aware, and that awareness allows us to know the cosmos in a way that nothing else in our corner of the universe can. Every fact we've explored raises more questions. That's the nature of discovery. The more we learn, the more we realize how much we don't know. Dark matter and dark energy compose most of the universe, but we don't know what they are. We don't know what's inside a black hole. We don't know if the multiverse exists. We don't know if we're alone. We don't know the ultimate fate of the universe with certainty. We stand on the edge of knowledge, peering into the darkness, catching glimpses of truth, but aware that the darkness is vast and full of mysteries. And that's what makes space so captivating. It's the ultimate frontier, not just of exploration but of understanding. It forces us to confront the limits of our knowledge and our existence. It humbles us with its scale and violence. It awes us with its beauty and complexity. It terrifies us with its indifference and its dangers. It inspires us with its mysteries and possibilities. When you look up at the night sky tonight, remember what you've heard. Remember that you're looking into the past, that the stars you see might already be dead. Remember that you're moving through space at over 1,000,000 miles per hour. Remember that the silence up there is absolute, that sound has no voice in the void. Remember that most of what exists is invisible to us, that we see only the faint outline of reality. Remember that time flows differently depending on where you are and how fast you're moving. Remember that the universe had a beginning and will have an end, and we exist in the brief moment between creation and dissolution. But also remember this: we have the privilege of awareness. We can ask why. We can seek answers. We can build instruments that extend our senses, telescopes that see across billions of light years, detectors that sense ripples in space-time itself. We can imagine what we cannot see. We can build models of reality and test them against observation. We can stand on a small world and comprehend the universe that contains it. Space is not just out there. It's in you. The atoms that make you were born in stars. The water in your cells was delivered by comets. The energy that powers your thoughts comes ultimately from the sun. You are part of the cosmos, not separate from it. When you study space, you're studying your own origins, your own nature, your own future. So keep looking up. Keep asking questions. Keep seeking the strange and beautiful truths hidden in the darkness. The universe is vast and mysterious and often terrifying, but it's also the only story that truly matters. The story of everything that is, was, or ever will be. And you, unlikely and improbable as it seems, are part of that story. You are the universe experiencing itself, a brief candle of consciousness in the cosmic dark. And perhaps, just perhaps, somewhere in the vastness of space, on a world circling a distant star, another consciousness is looking up at their sky, asking the same questions, feeling the same awe and dread, wondering if they're alone. Maybe we'll never meet. Maybe the distances are too vast, the timescales too long. Or maybe, in some distant future, our descendants will reach out and touch theirs, and two branches of cosmic awareness will recognize each other across the void. Until then, we have the stars, the questions, and the insatiable human drive to understand. We have telescopes pointed at the heavens, spacecraft venturing into the dark, and minds capable of grasping the infinite. We have the privilege of living in a time when we can see the cosmic microwave background, when we can detect gravitational waves, when we can image black holes, when we can discover planets around other stars. The universe is speaking to us in light and gravity, in radio waves and cosmic rays, in the subtle variations of quantum fields and the grand architecture of galaxy superclusters. Are we listening? Are we learning? Are we preserving this knowledge for those who come after us? These 30 facts are just the beginning, a glimpse through a keyhole into a vast mansion of reality. Each fact opens onto corridors of deeper questions, rooms full of mysteries, windows looking out onto vistas we can barely imagine. The mansion is the universe itself, and we've only explored a few rooms on the ground floor. What lies in the unexplored wings? What secrets are locked in rooms we haven't found? What views wait beyond windows we haven't reached? The universe is not finished revealing itself. New discoveries wait in the data streaming from our instruments, in the theories being developed by physicists and cosmologists, in the observations that will be made by future generations with better tools and deeper insights. Space is the ultimate adventure, the greatest mystery, the final frontier. It challenges us to be bold, to be curious, to be humble. It reminds us that we know so little, that we've only just begun to understand. And in that reminder is a gift, the knowledge that there's always more to discover, always another question to ask, always another wonder waiting in the darkness. So the next time you feel small beneath the stars, remember that you're part of something unimaginably vast and beautiful. You're a way for the universe to know itself. You're a pattern of atoms that can contemplate the cosmos that created those atoms. You're a temporary arrangement of matter that can appreciate the eternal laws governing that matter. You are, in the most literal sense, cosmic. And the universe, in all its terrifying beauty and beautiful terror, is your home, your origin, and your ultimate context. Everything you are, everything you've ever known, everyone you've ever loved, exists within the framework of space and time we've explored today. And that, perhaps, is the most profound fact of all. We are not observers of the universe. We are participants. We are the universe observing itself, asking questions of itself, marveling at itself. In your consciousness, the cosmos has opened its eyes. What will you do with that extraordinary gift?